Good evening, teacher. Today we are going to present our final project on the vehicular traffic model. This works presents the numerical simulation of a dynamic system composed of two ordinary differential equations using the explicit Euler method. The study evaluates the behavior of the system under variations of the parameters A and B and the nominal velocity Vn, with special attention to case where Vn less than 20. The results show that the value of Vn and the coefficient B directly influence the system's ability and time evolution, modifying of the overall trend, and final equilibrium of dependent variables. The Euler method is one of the simplest numerical techniques differential equations. Despite its simplicity, it is useful for the preliminary analysis of non-linear dynamic systems in engineering and physics. In this study, a model depends on three parameters, A, B, and Bn, is analyzed. These parameters regulate the system's response to definite initial conditions, and their adjustment allows for understanding how a nominal velocity below or above 20 units affects the system's behavior. The goal is to determine how the system trajectory changes as these parameters vary, providing insight into the stability and dynamic evolution of the model. This article presents a numerical simulation of a dynamic system model by two ordinary differential equations, solved using the explicit Euler method. The main goal presents a numerical simulation of a dynamic system model by two ordinary differential equations, solved using the explicit Euler method. The main goal is to analyze how the system behaves when three parameters are modified. First, we have A and B, which control the speed and stability of the system's response. They act as sensitivity or gain factors. Second, Bn, which represents the nominal or decided velocity of the vehicle. The simulation aims to understand how these parameters influence the trajectories of the dependent variables, helping to identify whether the system reaches a stable or unstable state under different velocity conditions.
Code implementation and methodology. The code used in the study follows a step-by-step numerical approach. It defines the differential equation describing the system time evolution using variables y in 0 and y in 1, which represent physical quantities such as velocity and position. It integrates the equation using the explicit Euler method with a time step h 0.01 over a total of 60 seconds. It tests several scenarios with varying parameters A, B, and Bn to observe the impact of h on the system behavior. It plots It plots the result of visibility, how the system evolves, and whether it reaches equilibrium. The method is simple but efficient for observing general trends in monolinear dynamic systems.
Relationship to vehicular traffic and conclusions. The relationship to vehicular traffic modeling lies in the analogy with vehicle tracking behavior. In real-world traffic, a vehicle's dynamics depend on its desired speed, Vn, the distance to vehicle ahead, and the reaction factor or sensitivity, V, which determines how quickly it adjusts its speed. In this context, y0 represents the vehicle's speed, y1 represents its position or distance relative to vehicle ahead, and Vn is the reference speed that the driver attempts to maintain. When Vn is less than 20, the system is stable. The vehicle smoothly converges to the desired speed. When Vn is equal to 13, the system becomes stable, similar to controller acceleration or unstable traffic flow. Therefore, this study demonstrated that the Euler method can effectively simulate vehicular dynamics and identify regions of stability in traffic models.